Hi everybody, welcome back to our reading of categories in Sheaves. We're picking up where we left off, this time with section 3.2. Section 3.2 in Kashiwara and Shapira is on filtrant categories. And it's mostly a collection, or really a section, dedicated to collecting results on recognition of specific conditions under which categories may be cofinal or filtrant, depending on the result, of course. And only the last lemma is sort of the critical lemma. I'll put the timestamp for that result in the description so that if you just want to see that one result, you'll be able to just click on the description and go there. But I debated not even doing a video on this section because after reading this section, I was not particularly amused. Most of the results felt like they were either obvious or, well, somewhat annoying to prove, not necessarily because they're hard, but just because working through them felt a little bit repetitive. I haven't yet seen too many great applications of these things, but I think of them as a collection of recognition results, and just like in our first algebra class, we learned a million theorems that tell us how to recognize properties of, say, groups. It does seem reasonable to have these theorems and to care about them, but I haven't seen any applications yet, so I don't really know how much we're going to need this. What I will say is that I'm going to work through some of these propositions for you. Some of them I'm going to skip. Some of them I'm going to just claim are trivial, and when I do claim that they're trivial, you should maybe go and check them yourself, either because we've already done them or because they are just, well, easy. And so without any further ado, let's just get into it. Our first result for this section actually is a triviality because I've proven all of these results already. So you should maybe take a moment and remind yourself why they're true, but none of them are new to us. And so the following conditions are examples of filtering categories. So first, any category with finite inductive limits. Second, any category with a terminal object. Three, a product of filtering categories. And finally, this isn't so much a property, but Kashiwara and Shapira included in the proposition. So maybe I should make it separate. And this is C filtrant implies C is connected. And I'm 99% sure I've proven all of these results before. Either I've proven them or I've remarked that they're easy, maybe elaborated on them a little bit. I've discussed these results, I think, so far. So the next result is an enhancement of a previous one. We saw in a previous video, back in section 2.5, we talked about cofinal functors. We give a characterization of cofinality there. And in particular, we have that if we have a functor from two categories, j to I, this guy is cofinal, in case you forget, when the category ji is connected for every I. In the case when j is filtrant, this can be enhanced. And this proposition we should work through in some amount of detail. So we'll spell out this proposition, not this particular statement, this is just me reminding you of a definition. But we're going to enhance this characterization when j is filtrant. So we have a proposition. Suppose J is filtrant, and phi j to I is a functor. Then the following are equivalent. First, phi cofinal. 2 ji is filtrant. And 3 is the following two conditions. So we have 3a, which says for each I, there is a j such endomorphism S I to phi of j, and b, for any I and j, and pair of parallel morphisms, I to phi of j. Then there's a morphism T j to k for some k in j, with the property that phi of t following s is the same as phi of t following s prime. Okay, so for this proposition, we're going to prove this in the reverse order. What I mean by that is oftentimes in these sorts of chains of arguments, you see people argue 1 implies 2 implies 3. We're going to argue 3 implies 2 implies 1. And the reason is because one of these propositions, or one of these claims, is trivial. In fact, 2 implies 1 is trivial because filtrant implies connected. We just said that. But in case you forget, filtrant implies connected. So we're going to do 3 implies 2 to get started. And this is relatively straightforward, although there's something to do. We're just going to check the definition. So to check the definition, we recall what we need. First, we need a non-emptiness condition. This is trivial. The first part of the A condition tells us that we have something, so we're done. For the next part, we have to consider morphisms S and S prime. And let's S and S prime go I to phi of j. Sorry, I should not put those next to each other because they're supposed to have different codomains. S I to phi of j, S prime, I to phi of j prime. Some different guy. Now, since j is filtrant, we can produce t and t prime, where t goes j to k, and t prime goes j prime to k. And this means that t and t prime allow us to, let me actually not get ahead of myself. So when I look at the second hypothesis, this guy B here, because of this sort of equalizing looking condition, I can apply this to the pairs phi of t following s and phi of t following, phi of t prime following s, and we can make these guys equal. So we get that phi of t following s is the same as phi of t prime following s. And that means that t and t prime, these guys induce morphisms in the category ji, which I'm going to abuse notation and use the same symbols. And so in particular, I can look at these. I can look again at these guys I to phi of j1, or sorry, these are I guess different, but it's fine. And I to phi of j2. These are going to be two objects of ji, and I can then consider two parallel arrows in this category, which I'll denote with Greek letters, we could call these guys C and eta, parallel arrows in Ji. And this means that we have a morphism J2 to J3 so that we can make these guys agree. And, oh, I guess I could label them. However, this means that the composition, which goes I to phi of J2 to phi of J3, must also define an object of J upper I by just ignoring the middle entry. But that means we have two possible compositions, both of the form like this. Really, I could put a second arrow here, but I just, it feels like it's a little bit confusing what that means, but it's okay. And these have to coincide. And so that concludes this part of the proof. So now, for the final implication, we note that, let's actually, I'm not going to put the box. The box would signify the end of the proof. So for the other implication, we note that since Ji is connected, it's not empty. So our first condition is trivial. So we only have to do the second bit. For this, suppose we have an I and I. I'll put a dotted line. That's how I'll separate them. And then we have an alpha. And then alpha should be a functor. Sorry, I got ahead of myself. My brain processing. Alpha functor J to set. Specifically, what this guy does is it takes J and sends it to Hom in I to phi of J. Now, the characterization we gave in 2.5 tells us that the limit of alpha is a singleton. This is because of the cofinality. Now, if we have a pair of parallel morphisms, S and S prime, I to phi of J, then we can look at what these guys represent. And in particular, S and S prime belong to alpha of J, which we just said is this Hom I phi of J. Helps when you put the parens in the right place. Now from the last section, what we saw is that this means that there's a morphism T, J to K. This guy, of course, lives in J. And such that S and S prime have the same image. And this finishes our proof. And this finishes our proof off. Okay, so as a remark, I want to point out that the third condition we have here makes it clear that I is filtrant when only one of the, of course, when any of these conditions are satisfied. So in particular, what we see is that cofinal functors out of filtrant categories have filtrant targets. Maybe I could have written filtrant J, but it's fine. Okay, so here's a corollary. Relatively easy corollary. I think this might be the last result that I'm going to work out for us in this section in any detail. Actually, no, I think not. I think one more. So, corollary. Suppose I is filtrant. Then, the first thing is, for any I in I, the category I upper little I is filtrant. And the functor, Kashiwara and Shapiro call it Ji, and they write it with like the plain J. I to I upper I to I, wow, that's a mouthful, is cofinal. And recall that this just means that it's the forgetful functor. It's the functor which eats, maybe I should call them rooted objects, objects that come with a specific map out of I, and it forgets what the basic map is and just remembers the object from I. And the other part of the corollary is that the diagonal functor delta is cofinal as well. And if you've never seen this before, like in topology or geometry or any of those branches of math where diagonal maps appear, then you should know that this guy takes an object I and sends it to II, like so. And it sends morphisms. What should I call this morphism? I don't know. F I to J, and sends this guy to FF, like so. Okay, this is not particularly difficult to prove, so we'll prove it. So for the first part, what you do is look at the part 2 of the previous proposition, and apply this to just the identity. This tells us that I upper I is filtrant. I think I called it 2, not Roman numeral 2. So that part's clear. Now for the interesting bit, that the forgetful functor, so to speak, I hesitate to call it that, but I guess that's what it is. I just get spooked because I think of the forgetful functor as like the thing that you do to, like, I don't know, groups, the thing that's got an adjunction with a free functor. And I don't think that really makes any sense in this setting, so I just get spooked. But I'm going to call it the forgetful functor because I don't know what else to call it. To check that this forgetful functor is filtrant, again, we just check the definitions. So suppose we have an I1, and then for any such I1, we know that there's a K and arrows. I guess I should say for any, I1, but also there's this specific I in the, I'm just getting a little tripped up in the notation. There's an I that's in the proposition, and I need to distinguish this from what I would normally just call I. So I'm going to call it I1, and then we have the specific I associated to the category I upper I. That's a mouthful in words, but I'm hoping that what I'm about to write makes it clear. So there's a K, and then there are morphisms I to K and I1 to K, because this is filtrant. So we have a morphism which goes I1 to the image of phi of I to K. Now, if I have an I1 and I and a U, where U is I to I2, then I can let S and S prime be a pair of maps, which go I1 to I2. And I can write this I can take this in particular to be phi of U I to I2. And these will be a pair of parallel arrows. Under this setup, there's a morphism, which we could call T, I2 to I3, such that the two compositions, I1 to I2 to I3, are equal. In other words, I'm just using this equalizing property. So that means that the induced morphism in I upper I, which if I was abusing notation, I would also call it T, but it's the composition I to I2 to I to I3 must coincide, where these are induced by U and T following U. And so in particular, if I call these guys T tilde, just to be a little bit clearer than previously, then we see that these satisfy phi of T tilde following S is equal to phi of T tilde following S prime. And that finishes the proof of this statement. Now for the second statement, we don't have to do very much. You just have to remember what these things mean and unwind the definition a little bit and observe that I, I1, I2 is isomorphic to I1, I2. And once you've convinced yourself of this, then we can just do the first part twice. And finally, we see that the diagonal functor is cofinal by the previous proposition. Okay, good. And that finishes our corollary. I realized that the notation kind of sucked throughout that corollary. I apologize for that. Like I said, I wasn't even originally intending to do a section for this. You guys should read this in Kashiwara and Shapira, or listen to me explain it as you feel you need it. Okay, one last proposition for now. And then I'm going to leave the rest of these results to you guys as mostly trivialities. So suppose we have phi j to I, a functor. This is our usual setup. Now we assume I is filtrant and phi is fully faithful, which I abbreviate as FF in our usual way. Now we assume further that for any I, there's a morphism I to phi of j for some j. In this case, j is also filtrant, and phi is cofinal. I don't know why I put 2 dots. And I like this argument. This is a very straightforward argument. Again, everything in this section is just the definitions. The non-emptiness part, that's always clear. In this argument, I'm just going to do the first part just for the sake of time. I feel like I've been talking for a little while already, and we're trying to keep this show on the road. So to that extent, let's just do the first bit. So suppose I have 2 objects, J1 and J2, in J. And since I is filtrant, there's an I in I, and morphisms, phi j1 to I, phi j2 to I, and by assumption, we have a j3, and a map I to phi of j3. And sort of the catch is that since phi is fully faithful, I can compose these guys, and then for either a equals 1 or 2, I can look at phi ja to I to phi of j3, and now I just grab my red pen and I sort of ignore this part and obtain a composition that goes this way. And now this must be the lift of something, or sorry, the image of something by fully faithfulness. And since that's the case, we've got the desired map in J. The cofinality, that bit comes from this second proposition we just proved. So I'm just going to say that cofinality is clear. Actually, second. From the second proposition. Okay. Okay, so the last thing I want to do before the lemma, well, there are 2 more propositions in the lemma, before the lemma, neither of which is very difficult, but both of which have quite a few parts, and that's annoying. And I think I've given you guys enough of the flavor of these arguments to see how they work, so that hopefully, if there's any doubt in your mind about how this stuff goes, you can fill in these blanks yourself. I mean, of course, you can always read what Kashiwara and Shapira say for yourself if you're super stuck, but I really do think that this is kind of straightforward. So let me just write down the statements of these propositions so that they're sort of recorded. That way, if I need to link back to them, I can say, by the way, here they are. But I don't think that it's sort of worth it for us to try to prove them, as they're all sort of simple. So here I'm going to just write trivialities / nuisances. And I'm just going to collect all these results here. So first, our setup is I have a composition like so, with two functors phi and psi, I, j, and k. I, j, and k all filtrant. Then in this case, for any j, ij to I is cofinal. Next, let me scroll. Thank you. Next, for any I to I phi I. Oops. Also cofinal. For any k, ik to jk, also cofinal. And lastly, for any u, k to psi of j, we have an induced functor, u star, which runs ij to ik. This is also cofinal. All of these things are straightforward definition chasing, and in fact, a bunch of them are even consequences of the others if you're careful about how the argument goes. For our next collection of not so difficult facts, actually this is just one fact, so I'll just call it here, just put it in the list. We have, this one's a proposition on its own though, so I'll single it out a little bit as number 5. If I is filtrant, then I is cofinally small if and only if there is a small subset S of the objects such that for any I, there is a morphism I to j, j and s. Okay. And also, again, not tremendously difficult. In fact, this is sort of highly plausible. Remember that cofinally small means that you're linked by to some small category. So in other words, sort of maybe if you like residually small is one way to think about what this is saying. And of course, all this is saying is if there's some sort of small core bit of this category that you always map to, then even if you're not small yourself, then every object there sort of maps onto this some part of this sort of small core of this guy. Okay, now let's get to the important lemma here. This is the key result of this section. I've been talking for a long time. So let's see if we can wrap this up. So let's suppose that I is a small ordered set. And alpha, I to C, some functor. Now we use this italic j here, which hopefully looks different enough from my ordinary j, be the set of finite subsets of I. And we equip j with an order. In particular, we order j by inclusion. then to each j and j, wow, that really doesn't look very different at all. To each ordinary set j in our fancy j, we have the restriction, alpha j, which goes j to c, and the claim is that j is small and filtrant. The fancy j is small filtrant, and we get a formula which says that the limit of alpha is the same thing as the limit over the j in fancy j of the restrictions of the alpha j. And this is a really important result, because as Kashiwara and Shapira tell us, we can sort of use this we can rephrase this lemma in an important way. And I won't bother to write this down because I don't feel I need to write the same lemma right beneath this one. But what you should think about this as telling me is, if I have a category which I could call C with small filtrant inductive limits and finite inductive limits, then I can put these together, and C then has small inductive limits. I realize that was a bit of a mouthful, but the important thing here to understand this, just sort of look at what this formula is saying. I'm taking the limit of alpha and I'm decomposing it into a limit over this category J, and we're seeing that J is small and filtrant, and then the limit over the restrictions, where this restriction then is just a finite inductive limit, because all these J's are in particular finite sets. So the consequence of this is that if I have a functor which commutes with these two categories, in particular, category is a loaded word here, but it commutes with these two classes of limits, the small filtrant inductive limits and the finite inductive limits, then it commutes with all small inductive limits, period. And in particular, you can specialize this to whatever class of limits you're interested in that's more specialized if you need to. Okay, now let's see if we can finish this off for the video with the proof. So that J is small and filtrant is clear. That's just set theory. We're dealing with finite sets, and it's just a cardinality argument to see that. So smallness is clear. Filtrant is also clear from the definition because everything is done by inclusion. So really what we're trying to do here is prove the isomorphism. So to that end, what you should do is take the set K of ordered subsets of I cross fancy J, consisting of pairs IJ with I and J. I think of this as like the tautological subset here. I don't know, like it tickles the geometry part of my brain to look at sets of this form. Also, we haven't done any geometry in this video series in a long time, and I'm very sorry for that. The important thing about this collection is that there's a projection to the first factor, which Kashiwara and Shapira call phi. I don't know why they don't call it pi, but I can project to the first factor k to I. And this functor is cofinal. To see that, just note that if I have some I0, then I can consider k I0, and this is nothing but the pairs of I and J, with I0 less than I in this ordering. But then for any such pair, ij in k upper I0, then what this means is, well, maybe even less than that, sort of trivially, I and j must be less than I and j union I0 by definition, just from what the order is. But also, we know that I0 together with the set I0, which is of course a perfectly valid set, is going to be less than I together with J union I0. Sorry, that should be like so. Okay, so sorry, I just realized that's a capital I. That shouldn't be. This should be an I0 as well. There's no capital I anywhere in this, so that doesn't make any sense. Okay, and so that proves the connectedness. So what we've shown here is that I can link anything to anything else, one way or the other, and so we've established the connectedness of this upper index category, which by the first result that we had in this section, that handles the filtrancy. Filteredness? I don't care. Now we have to do the isomorphism, and for that we're going to calculate. So what we see is that we're interested in this limit of alpha. This is, of course, the same thing as the limit of alpha following phi. And this can be written as lim over j in fancy j, lim k in k lower j, alpha of phi k. The first one of these, so in case this isn't super clear, the first argument here, this is a property of cofinal functors. We saw this back in section 2.5. And the second is our formula for limits. So what we need to do then is notice that I've got the outside term right, because I've got the limit over the j and j. So now what I want to do is rewrite the inside term so that I can identify it with the limit of the alpha sub j's. And that's basically all that's left. Okay, so how do I do this? I remember now. Sorry, I have to do this, make sure I've got this in my brain. We consider the functor Cj, j to k, which takes j and sends it to the set j, j. This functor is cofinal. You can see this sort of by staring at it. If I take any k, little k, which would be the unordered pair of the form j1, big J1, sorry about that, backed up too far, then J1 will be in J1, which is a subset of J, and this implies in particular that J upper K is our set of J and J, where J1 is less than or equal to J, and this is connected. Sorry, that came out a little bit garbled, but I think you guys know what I mean. This is, of course, since J1 here is chosen to be our smallest element. Okay, so now we need to consider this limit k in kj. Sorry, that's the wrong j. It should be big J. Of alpha composed phi k. But from the previous part, this is, of course, the same thing as the limit of alpha composed with phi composed with Cj, but this guy is, of course, the limit of alpha j, alpha sub j, just by definition, which is what I wanted to prove. So we're finally finished. Whew! All right, that felt like it was painful, and it took a while for us to work through everything. So I'm sorry if that's the case. But, we finally got this painful section out of the way, and we pick up next time with a discussion of exact functors. And I'm already curious because the definition of exactness that they give is already quite interesting. So there will be something to unravel right off the bat. All right, guys. Till the next time, take care.